Good morning, everyone. Today we will switch to another topic, which is thermodynamic. We'll start with this chapter, temperature, heat, and we will discuss the first law of thermodynamics. These are the concepts that we'll talk about, shown here in the figure. So let's start. When we talk about thermodynamics, when you see the word thermodynamics, we see that there are two terms actually, thermo, which when we say thermo, we think about temperature, heat, and dynamics. Dynamics means motion. So there is heat and there is motion. Okay? Look at this picture, that's basically just boiling water. You are heating the water and you are close to the boiling point. Right? You see a bubble of gas, you see liquids, but you see also things are moving. Okay? When you heat liquids, you see movement, you see motion. Where does this come? It comes from something called internal energy. So any system has an internal energy. Internal energy of water, basically, what is that? That's the kinetic energy of all molecules of water. We'll talk about it when we evoke the first law of thermodynamics. In thermodynamics also, it's very important to know what we are studying. Okay? It's important to define the system that we are studying. Are we studying the water? Are we studying the water with the glass here, with the heater? So what is our system that we want to study? Once we define our system, we know the boundary of that system. So we will know what is the surrounding, what is the environment on which this system is. And we should know what are the properties of the system. The system exchange energy with the outside, or is it isolated? With thermodynamics, there are a lot of variables. Basically, any sample property, any material property can be calculated thermodynamically. But what we are interested in first is temperature, pressure, volume, and the amount of the object, basically the mass or number of moles. Another important parameter is the state of the matter. Are we talking about liquid state, solid state, gas state, or a mixture of different states? So before starting, we need to define something called thermal equilibrium. Okay. Without this thermal equilibrium, we cannot define any sample parameter thermodynamically. If I take a hot coffee inside a thermos, I can define a temperature, I can associate a temperature to it. Okay? The coffee inside the thermos is at thermal equilibrium. When we start to pour coffee into a cup here, so we have a hot coffee, that's how I like to drink it, but this hot coffee is not at thermal equilibrium. While it keeps exchanging heat with the environment, with air, but also with the cup. So, can we define a precise temperature to that? Probably not. Probably if you are inside, the coffee is still hot. If you are just outside, well, the coffee is more cool because it is exchanging the heat with the outside. So the molecule of this coffee, the particle of this coffee, they don't have the same temperature. So we cannot define a temperature for the whole coffee. Okay, so we say that this coffee is not at thermal equilibrium. What it is needed to be at thermal equilibrium, well, we need to wait longer. When the temperature of the coffee settles down. Okay, it keeps exchanging heat with the environment, and it will reach a certain stable temperature. I don't like to drink it at this state, but that's what we call thermal equilibrium. At this point, I can associate a temperature to this coffee. So there is a relationship between thermal equilibrium and being able to define a temperature. Now let's go to zeroth law of thermodynamics. Why zeroth law? Simply because people, they make a first law of thermodynamics, second law of thermodynamics, even the third law of thermodynamics, but after they come back and they say, oh, we need to agree on something first, and this agreement, they call it zeroth law of thermodynamics. There is another reason for me, because zeroth law of thermodynamics is not just common sense. What it states? It states that if two systems are each in thermal equilibrium, we just learned what is thermal equilibrium before, with a third system, then they are in thermal equilibrium with one another. So it means if I have a system A in thermal equilibrium with system B, and the same system A is in thermal equilibrium with system C, we can deduce that system B is in thermal equilibrium with system C. That's really common sense. And this is what we call zeroth law of thermodynamics. But it turned out to be a very important statement, because without this we cannot define temperature. We cannot define temperature. So the most important consequence here, if two systems, B and C, that they don't see each other, are in thermal equilibrium with one another, if they are in thermal equilibrium, so they don't see each other, but they are at thermal equilibrium, then they have the same temperature. That's the most important conclusion here. Because it turned out not to be important fundamentally, but also practically. With that, we can invent thermometer. How is that? We have two systems, isolated. They don't see each other. Okay? Maybe one in Oman, the other one in USA. Let's say. And we have a third system, which is a thermometer that we agreed on. Thermometer is in equilibrium with A, so we reach a thermal equilibrium and we read the temperature of A. I take the same system T in contact with B, we reach a thermal equilibrium and we read the same reading. So it means A and B, they have the same temperature. That's practical conclusion. And this comes from the zeroth law. So we can start building our thermometer. How we are going to do that? So people noticed that things expand and contract also, by the way, by temperature. If I raise temperature, things expand. So we can take a rod of length L at temperature T. If I increase the temperature a little bit, I will see expansion of the length. Fine. But not only solid, liquid also expand. Right? So with that, we can build our thermometer. How we will do that? So thermometer looks like that. Here we have different scale. We'll talk about it later. So that's degrees Celsius, that degree Fahrenheit, that's Kelvin. All right. So we have inside liquid basically mercury. That's what we are using. And well, if I increase temperature, the liquid will expand a lot. Yeah. Okay, so there is a very narrow tube here. In this tube, the expansion will be much visible and easy to read. So how we can calibrate now our thermometer? Well, we can put this thermometer in water and decrease temperature until we reach freezing point of water. How we know the freezing point of water? Well, basically when water and ice coexist and they are both at thermal equilibrium. That's my freezing point at 0 degrees Celsius. So I can mark here 0 degrees Celsius. Also, I can take the same water and go to the boiling point. Boiling point, basically what is it? When vapor and water coexist. Okay? And that's happen at 100 degrees Celsius. So we have a 2-point here, 0 and 100, and after it's easy to finish the graduation. Basically, the expansion, we can assume it to be linear expansion. But if you have different liquid, well, you can have certain disagreement in reading of temperature. So the best system to build proper thermometer is gas. It's not liquid, it's not solid, it's gas. All right. So that's schematic of what we call constant volume gas thermometer. So I will not talk about design, that's out of the scope. There is a certain quantity of the gas, which is pressure times volume. The pressure by times volume, it happens to vary linearly with temperature. Okay? V equal to what? Or nRT. Okay? That's for something called ideal gas. All right. So first, what do we mean by ideal gas? Ideal gas, it means a very dilute gas. So with low concentration, it means that the particle of gas, the molecule of gas, are far away from each other and they don't interact. When you reach this point, you can write this ideal gas equation. So P, that's pressure, V is volume, that's the product of pressure with volume, is equal to what? N, and N, that's the number of moles. And T, that's temperature in Kelvin. Okay? And R, that's a gas constant. Gas constant. All right. So all gases, if they are dilute enough, you will see that this graph is just a line. So we can define this to be 0 degrees Celsius, and we can define that to be 100 degrees Celsius, and we can graduate like this our thermometer. It turns out that this kind of gas thermometer, if you use different gases, if they are dilute enough, you will have quite agreement in reading of temperature. But there is another important point here. So all the lines are, all the curves are linear. If we extend these lines, it turns out that they cross the x-axis at one point. Okay? This point, it happened to be minus 273.15 degrees Celsius. That's what we call absolute zero. So why we call it absolute zero? Let's say, can we cross here the x-axis in the negative side? What it means crossing the x-axis in the negative side, why it cannot be here, for example? Being at this point, it means I have the product of P times V is negative. But can we have that? Can we have a volume negative? That doesn't make sense. Can we have a pressure negative? That doesn't make sense too. Pressure is always positive. So this product PV is always positive. What it means, that's the smallest temperature that we can achieve. Okay? And it turned out that all gas thermometer will go to the same point here. So this point is called absolute zero, that's 0 Kelvin, or we write it simply 0 K. So that's 0, that's not okay, that's 0 K. So that's our reference point. 0 degree and 100 degrees Celsius are not really quite reference point. Why is that? So we might think that this is freezing point of water, and this is the boiling point of water. But freezing point, for example, of water is 0 degree only at atmospheric pressure. If you go higher in altitude and you change the pressure, the water will not freeze at 0 degree. It will freeze at different temperature. So these are not good reference points. The second reference point, it turned out in this graph to be very close to 0 degree. In fact, for water, in fact, 0.001 degrees Celsius. What's this point? And why it's a reference? Well, here I'm talking just about water. Water in different states, ice, liquid, and steam, vapor. So this is what we call a phase diagram of water. That's pressure versus temperature. And this is where we live here. This is what we are used to. That's 1 atmosphere. Okay? So this line is the line where we usually see things happening. So basically, water freeze at 0 degrees Celsius and boil at 100 degrees Celsius. But when you change pressure, as you can see here, if you go away from this 1 atmosphere, the freezing point and the boiling point, if you take another pressure here, the boiling point of water, for example, is not 100 degrees, much less than that. The most important thing here is this point. What is this point? That's what we call triple point of water. And it's important because the water exists in this point in 3 forms, in 3 states. That's the coexistence of liquid, gas, and solid. In other words, ice, liquid water, and steam or vapor all coexist at the same point. And this had happened at 0.01 degree Celsius. Okay? And it happened at almost 0.6% of the atmospheric pressure. Here in the image, and you can see the link in the video that show the triple point of water. So basically what we can see here is ice, water liquid, and some bubbles of gas. Okay, so I shared with you the video to see the water at this point. So here I summarize the 3 scales. So that's the Kelvin scales. That's basically the more scientific one that scientific community agreed to work with. We have also degrees Celsius that we will use a lot in this chapter. And we have degree Fahrenheit. And these equations are a relationship to go from the Kelvin. So whatever you see here, T is in Kelvin, to temperature in degrees Celsius or temperature in Fahrenheit. So this is basically how to go from degrees Celsius to Fahrenheit, to degree Fahrenheit. We say degree Celsius, degree Fahrenheit, but we don't say degree Kelvin, we say just Kelvin. Okay? Most important things here, how to go from, in this course, how to go from degree Celsius to Kelvin. So basically, just you remove 273.15 Kelvin, but for practical reason, we will forget about this point for 15. Okay? So basically, what is 0 Kelvin? That's, if you want to put it, but me generally I don't put it. So 0 Kelvin, that's minus 273 Kelvin, degree Celsius. What is, for example, 100 degrees Celsius, the boiling point of water? So I will just add 100 to 273, so that's 373 Kelvin. What is the room temperature? 25 degrees Celsius. Well, 25, you add just 25 to that, so you get 298 Kelvin. Okay, so that's the way how we go from degree to Kelvin and vice versa.